Now, so since this is an integrator, if our input is a square wave, our expected output will be a triangular wave, right? So, okay. So if our input here is a sine wave, we are going to expect that the output should be a cosine wave. So that's why it is called an integrator. Now there is another configuration which is called a differential amplifier, right? Differential amplifier is a device that amplifies the difference between the 2 points but rejects any signal common to the 2 points. Take note of this, rejects any signal common to the 2 points. We have here B1, B2, R1, R2, R3 connected to the op-amp. So let us take KCL at node A first. Let us derive the general equation for this. B1 minus BA is equal to BA minus BO, right? Divided by R2. So this current here will be equal to this current, right? This current here will be equal to this current. So we will have this equation. So simplifying this equation, we have B out is equal to R2 over R1 plus 1 multiplied by BA minus R2 over R1 B1, right? Now let us try to again apply KCL at node B, at this node. So we will have B2 minus BB over R3 will be equal to BB minus 0 over R4. Okay? So now solving for BB, we will have R4 over R3 plus R4 multiplied by B2. But in this case, we have BA equal to BB. Okay? So BA equal to BB. So we have to substitute this part of the equation into this, right? So now we will arrive in this equation that B out is equal to R2 over R1 plus 1 multiplied with R4 over R3 plus 4 multiplied by B2 minus R2 over R1 B1. So simplifying further this equation will be B out is equal to R2 multiplied by 1 plus R1 R2 divided by R1 1 plus R3 over R4 multiplied by B2 minus R2 minus R. So let us try to how it becomes like this. Let us try to derive. So we arrive at this equation, but we had arrived again after simplifying this. We arrive in this equation. So we want to derive this equation based from this. So from here you can see that this portion here is R2 over R1 multiplied by 1. Okay, I copied it here, right? R2 over R1 plus 1, R4, R3 plus R4 B2 minus. So I can rewrite this part of the equation here in terms of I will put R2 out, R2 over R1 outside, and I will factor out 1, okay, plus R1 over R2, right? It will cancel out each other. It will become 1 here. That's why this one is equivalent to this one. Okay, what about here? I can bring R4 at the bottom, R3 plus R4, right? So this is equivalent. This portion here is equivalent here, and here I did not change anything. So after that I have here from the numerator, this will become at the numerator 1 over R1 plus R2 divided by, I can simplify this portion here into 1 plus R3 R4, right? 1 plus R3 R4 times B2 minus R2 R1 times B1, right? Which is equivalent now to this part of the equation, right? Okay? No, sorry, to this one, to this part. It's equivalent to this part of the equation. Okay, now, since the difference amplifier must reject signal common to the two input, the amplifier must have the property of B out equal to 0 when B1 is equal to B2. So when B1 here is equal to B2, the output should be 0, right? And this property exists only when the ratio of R1 over R2 equal to R3 over R4, right? When R1 over R2 is equal to R3 over R4, the output will be 0. So, from this equation here, if R1 equal to R2, R1 over R2 is equal to R3 over R4, then this value here can be cancelled, right? We can cancel this one because 1 plus R1 R2, 1 plus R3 R4 will be equal. We can cancel this one out. So the only thing remaining is R2 here multiplied by B2. We can factor out R2. So we arrive in this equation, R2 multiplied by B2 minus B1, right? But if R2 is equal to R1 and R3 equal to R4, we can also cancel this R1 over R2. We have B output. This is a special case when R2 equal to R1. We will have the differential voltage B out is equal to B2 over minus B1. Okay? But this is the general equation for the operational amplifier or for the differential amplifier. Okay? In next video, we're going to perform the lab experiment using the PSPice.